All starts. Let's hope that we can get through all of this today with no interruptions. I am just waiting because I think any second they're going to come through on the announcements and say, due to the accident on the veterans, we're supposed to let all these kids in late. But we'll see. We'll see. So I was talking about the Earth the other day, and in that discussion, I asked you guys to calculate its rotational speed. So if we bring the Earth back up here, we look at the fact that it's spinning, and I said that we had to calculate the rotational speed. You guys took the one rotation every 24 hours and converted that into an angular speed. And I think you got 7 point, what'd you get, 7 point what? 7.27? So I was going to put 7.3 times 10 to the negative fifth, and that's radians per second. It's the rotational speed of the Earth. I then ask you to go a little bit further and calculate how fast a person who is standing on the Earth is traveling, what their, we talked about some vocabulary here, what their tangential velocity would be. Be prepared for me to use the word linear and tangential in both your test and in our discussion, just kind of hand in hand. So this is how fast they're moving in meters per second. And I also indicated to you guys that, and if you want to make that calculation, the easiest way to do so is to consider that there is a direct relationship between all of the angular variables and their linear counterparts. And if you want to move from one to the other, you merely multiply by the radius. Now, this is one of those things where that's not an X, that's a times symbol. So I don't want you to get that wrong in your notes. Make sure you know I'm talking about times. Now, you've been taught this, but you weren't taught this in a way that you could easily bring back up. It was in geometry, and you would talk about arc lengths, and you would talk about sectors. Those words might be foreign to you, but it was something that was part of the discussion that you had. And it was something usually like that the arc length, they would use S, is equal to the angle measure times the radius. This was in your geometry class. And if you don't remember that, then think back to just elementary school where you knew circumference was equal to 2 pi times the radius. That does sound familiar, right? Well, circumference is a displacement. If you roll a wheel one circumference, then it will roll one rotation times the radius. How far is one rotation in radians? 2 pi, that's right. So the definition of circumference is where we get this from. And we can apply it across the board to all of the measurements. You divide this equation by t, and now you have angular speed and linear speed. Divided by t again, and you've got angular acceleration and linear acceleration. So this moving back and forth between angular and linear properties is something that you're going to have to be able to be accustomed to doing. We don't do a lot of it, but we are going to practice a little bit here. Now, I did want you to find out how fast we are traveling, being that we are near the equator, which means we need the radius of the Earth to do so. And I'm not sure which class I was able to get it out. So the radius of the Earth is 6.38 times 10 to the 6th meters. That is the radius of the Earth. Now, it's just a hop, a skip, and a jump to tell me what the linear speed is then. Now, take a few minutes, grab your calculators, carefully type this in, making sure to use scientific notation correctly. And I don't assume you guys know how to do scientific notation, so look above the 7 key and find that EE button, because that's how you type in scientific notation. Yeah?
So that one equation with the circumference, if you divide it by time, then you get angular speed.
Yeah.
And if you divide it by time again, you get angular acceleration.
Right.
Okay.
Yeah, because, I mean, it's displacement divided by time is speed, and velocity divided by time is acceleration. All right, so to type these in, I'm just looking at the top one. You're going to type in 7.3, and then it's going to look like EE to the -5. That's how it should look when you're putting it in your calculator. Please do not ever use the 10 with the X on it for scientific notation. If you're doing the anti-logarithm, you use that button. But this is an operation in your calculator. Your calculator stores it differently. Your order of operations will get screwed up if you're not careful. Please use the EE button. It works correctly. So, the number you're going to get, you might not, I don't know if you have any idea whether it's a big number or a small number. Does anybody have it written down yet? Somewhere in the 400s, 465? That's it. 465 meters per second. So, big number or small number? Yeah. To put it in perspective, the speed of sound is 330 meters per second, which means that near the surface of the Earth, near the equator, everything on the Earth is moving faster than the speed of sound. This isn't a small amount. This is why we launch rockets near the equator, because they're already moving this fast. It saves us almost 10% of the fuel necessary to get to orbit by launching near the equator, as opposed to launching closer to one of the poles. The cosmodrome that the Soviet Union has to use requires that they use more fuel for the same launches that we can do near the equator. So this is not inconsequential. You wonder why we have such turbulent weather and why weathermen can never figure it out? That's because every piece of landmass is moving at this speed too. All the mountains, the air is being stirred continuously by a spoon traveling through the air at 465 meters per second. So people wonder why the jet stream is so erratic and why it moves so much, and why small amounts of temperature variation cause such big disruption. It's because the air is actually moving really fast. The whole thing is moving really fast. We don't experience it, but if the Earth were to suddenly stop moving, we'd all be smashed up against that wall over there. So this amount is actually pretty extreme. Now, we are actually not traveling this fast because we are not at the equator. If you want to know how fast we are traveling, you need to know what latitude we're at. I don't know what latitude we're at, do you? I could look it up, but it's just not worthwhile doing. It's over there. So it's going to stay over there. It's just the sign of the latitude. I don't know what it is. So it ends up being like 420 meters per second. So it's not like a massive difference here in Florida. Now, New York, yeah, Canada, they're not moving as much. All right. Any question on where we came up with this calculation? Yes, ma'am.
How did you get 465?
I multiplied 7.3 times 10 to the -5th times 6.38 times 10 to the 6th. That's why I drew that line and put the time symbol there. I didn't want to put it in a row, but all I used was that the linear velocity is equal to the angular speed times the radius. That's what I used. Does that make sense? Uh-huh. Now, without moving away from this too much, we are going to practice this a little bit. You can see how it's, some of these problems might sound. I'm not going to pick anything all tremendously difficult. And I want you to be kind of prepared for these kinds of problems, but they're not too tough. Let's think of a carousel with a couple of horses on it. I think I used this yesterday. So I have a carousel. And the first horse is 1 meter away from the center. And the last horse is 4 meters away from the center. That makes sense, okay? No big deal? So again, there's a total of 10 pieces of possible information. I think from the problem, you can identify 4 of them. I don't think it's obvious, but I think you can. Try Try and identify the 4 pieces of given information. One of the pieces that was given. Yes, sir?
Final angular velocity is 1 rotation every 3 seconds.
That's right. The final angular velocity is 1 rotation every 3 seconds. So to express that, 1 rotation every 3 seconds. It's still going to be distance over time. We're told it's traveling in a circle and makes 1 rotation every 3 seconds, just like the Earth. 1 rotation every 24 hours. That was its angular speed. So they gave the final velocity. They just didn't give it in a manner that you'd be used to. And be prepared. They're not going to say it's 4 radians per second. Not going to be that obvious. They're going to be a little more sneaky at it. Now, the first thing you probably should do before we go on then is figure out how many radians per second that is. Because it's almost always best to do this in radians per second. And if you don't know how to do that, please don't be sad. It's not hard. But you should just be clear. If you don't know how to do it, remember 1 rotation over 3 seconds. You can convert to radians by using a unit multiplier. Something that will cancel out the rotations, so I need it in the bottom, and leave you with radians. So I need radians in the top. So how many radians are in 1 rotation? 2 pi. Now, you guys love to leave pi in your answers. You can knock that off in here. The top is 6.28. Right? 2 times 3.14, 6.28. And I'm dividing it by 3. So I'm going to get an answer like 2 with some change. I think it's always best to know what you should expect your answer to be before you start, especially dealing with radians, because you guys are going to make a mistake here in a few minutes, and I won't call you out on it, but I need you to be thinking about what the answer size should be. So tell me, 2 point what? 2.1 radians per second. All right. When you're given a value for a rotation, please just put it in radians so you have it available, because you're probably going to use it. And it only takes a second. You're talking about multiplying or dividing by 2 pi. Now, we have more information than that. Could somebody name one more thing we have, at least? Yes, sir?
I know if you multiply the 2.1 like radians per second by 4, which is the radius, it should give you the other velocity.
Well, you're right. I could consider that the linear velocity, but there's 2 possible linear velocities, right? There's the inside person and the outside person. So the outside person I have to multiply by 4, and the inside person I have to multiply by 1. Right? The inside person is 1 meter away, that's their radius, and the outside person is 4 meters away, that's their radius. So yeah, we could write this as 2.1 times 1 meter, or 2.1 meters per second for the inside person. And then I could take my 2.1, multiply by 4 meters, and get 8.4 meters per second for the outside person. Right? There's 2 people, they have 2 different linear speeds. This person and this person. The linear speed is the angular speed times the radius. I want to be on the outside. Looks like it's more fun. Okay, there's more. Because to actually solve any of the motion problems, I have to have at least 3 pieces in one of these columns. 3 of the motion variables, and right now I only have 2. Yes, ma'am?
Is the initial angular velocity going to be 0?
Yeah. Every time I've been on one of these stupid things, they start from rest. In fact, they really yell at you when you get on it while it's moving. And try it. They get all uppity. Jump over that little railing, come yelling at you. Especially at Busch Gardens. Busch Gardens, they get really mad. Security guys come out. So yeah, I think we can say the initial velocity is 0. That probably makes it pretty easy to figure out each person's initial velocity. I think we can probably say it's 0 over there too. All right, now we can solve a problem. We have 3 motion variables. So now we can start hitting the motion problems. For example, the first one, what was the angular acceleration? If I want the angular acceleration, I'm going to need to consider a relationship that has these 4 things together in it. Now, I am completely out of space to be able to write here. So I'm going to flip back and forth, but I'm noticing in my head here I've got initial velocity, final velocity, acceleration, and time. So the questions I gave, question 2 says, how many rotations while speeding up? Well, that means I'm going to have to convert back from radians back to rotations. Why did I convert in the first place? Probably more for things like question 3 and question 4, where I'm definitely asking for a linear answer, and I would have needed the radians to get that. Does that make sense?
Yeah.
And I understand, you know, it's hard to see why you would do the unnecessary work. It's just because I have found that students forget to do that step, so I try to make us very conscious of the step when I talk about it. Yes, sir?
Couldn't you calculate the angular displacement by calculating the circumference of the circle?
Well, that's, you could. And I'm going to be very, very over the top here and say that there's probably dozens of different ways we could do these in dozens of different orders. We could do everything from linear and then convert back to angular at the end. We could do what you subscribe to, which is the idea of just knowing what the circumference is and multiplying and dividing by a circumference all the time. All of these work. Other questions? Now, I'll be honest. I am looking at something in the future. And just because... Now, I don't want to spend the entire day doing one motion problem, but I am being very slow and deliberate. That's kind of purposeful so that I can try and answer all of these questions as they come up. But do you see how the rest of these are really going to be stuff we've already done before? I mean, how many rotations while speeding up? All right, I need this in rotations. Can I figure out 3 pieces of information I can use to figure that out? Well, sure, I have 3 pieces already expressed there. Can I solve for it? Sure. I can do that. You take a look at these. How far did each of them travel? You know how many radians they moved. You need to multiply by the radius to get their distance. Number 4, compare the tangential acceleration. You know the angular acceleration was 0.21 radians per second squared. Now calculate the linear accelerations. The word tangential means linear. Okay? Practice. Things have been a little bit convoluted. I want you to think about this for the future. We talked about torque already, right? Torque is actually proportional to alpha, but only if this is in radians per second squared. Remember I was talking about energy? There's rotational kinetic energy. It is proportional to omega squared, but only if omega is in radians per second. There's angular momentum, capital L. I know, makes a lot of sense. Linear momentum's a P, angular momentum's an L. Can't help you, but just understand that it's capital L. It is proportional to the angular speed, but only if it's radians per second. So I do have something that's going to be happening in the future where putting your values in radians is going to be necessary. Does that make sense to all of you? So that I'm working towards a future where we'll have to use all 3 of these. And that's why I'm kind of just being, let's just go for radians from the beginning. And omega final equals alpha times t plus omega initial. I didn't make it up. I memorized the 5 motion variables and the 5 motion equations. And since v final equals at plus v initial, I just kind of translated it into angular. That's all I have to do. So 2.1 equals alpha times 10 plus 0. I took the stuff from the three pieces I knew, plugged it in for each of the things that I was missing, and then I just had to find alpha. So divide both sides by 10, and the answer will be in radians per second squared. Yes, ma'am.
Why exactly do you have to change from rotations to seconds to radians per second?
I don't. Unless I need to convert to a linear quantity, or unless they specifically ask for radians, you could have left your angular acceleration in rotations per second squared.
And it would have been like, well, if,
It would have been accepted if it was not specified that you had to change it. Now, the reason why I had us convert to radians, and I'm just going to be honest with all of you, and this might be worth putting a note down. You'll never be wrong if you're using radians in the middle of your problem. Because you might be converting back and forth from linear to angular. And you won't be wrong if you're using radians. You will if you're using rotations. So I encourage you, if you know your problem is going to have you switch back and forth, to just go ahead and start in radians. But you bring up a good point, because when I go back and look, I'm going to think of an equation that has everything in it except for acceleration. I mean, even though I have the acceleration right here, you know me, I like to use what was given. So that's going to be delta theta equals 1/2 times omega initial plus omega final times t. Looks familiar, right? I have everything. I have 0 plus 2.1 times 10. And when I work all this out, 21 divided by 2 is going to be 10.5. So delta theta equals 10.5, and this will be in radians. So this is not my answer, because they asked how many rotations did the wheel make. So I have to convert it. I want rotations. I had radians. So 1 rotation is 2 pi radians. Now don't use your calculator. How many radians is 2 pi?
6.28.
Okay, so 10 divided by 6 is going to be a little less than 2, right? All right, use your calculator real quick. And don't let anybody see your answer. Just do 10.5 divided by 2 pi. Again, don't let anybody see your answer. Because some of you have like 15 or 16 as your answer. And this is why I'm telling you to think about what the answer should be before you grab your calculator. Look, if you did 10.5 divided by 2 pi, if that's what you typed in and hit enter, you told your calculator to do 10.5 divided by 2 times 3.14. That's what you told your calculator. Because your calculator obeys strict order of operation. You didn't tell it to put both of those in the denominator. You didn't put parentheses around it, which is why you got the wrong answer. Now, you might have known to do that. You were just in a hurry and you weren't thinking about it, but how often will that happen on a test? 22 years of doing this, it happens to a lot of you. And this isn't the only place where 2 pi shows up like this. It shows up all over the place. So please think about what your answer should be. And if you get 15 when you're supposed to get a number less than 2, perhaps slow down and put parentheses around your 2 pi. Because that will fix it. So if you didn't have this problem and you know what you're doing, what's my answer then? 1 point what?
6.7.
Rotations. Now, I'll be honest, I can keep doing the rest of this problem. Are we really done with this? Do you need to see the rest of this done? I can, but I just don't want to because it's just the same stuff as first semester, and I'm kind of done with that stuff. So my expectation here is